What's up, folks? This is Ref Bari, Brown University physics graduate student. Today, I'm bringing to you an amazing topic which you might have not thought about before. Let me ask you a question. Why do magnets exist and how do they work? To answer that question, we need to zoom in to the atomic level. So let's do that. Consider an atom. Now, an atom is composed of three main subatomic particles. We've got protons and neutrons in the nucleus, and we've got, yikes, electrons orbiting the nucleus. Now, each one of these subatomic particles has something called spin. Now, what is spin? Spin is something very peculiar to the quantum world. Say we have an electron right here. Here's an electron. This electron, if you measure its angular momentum experimentally, it seems to indicate that the electron is spinning around like this. Now, in reality, if the electron was actually spinning around, its surface would have to spin faster than the speed of light. So we know that in reality, the electron is not actually spinning to generate that angular momentum. The truth is, physicists still don't know how electrons generate this angular momentum without spinning. But let's just pretend for a second that the electron is indeed spinning. Well, then what would the consequences be? Well, if the electron is spinning, you've got a circulating circle of current. And Faraday's law tells us that a changing electric field, well, generates a magnetic field. In other words, every electron in the universe has a tiny magnetic field associated with it. In other words, every electron in the universe is like a tiny magnet. Every electron has a tiny magnetic moment. Okay, well then, why isn't every object magnetic? Why isn't this blackboard magnetic? Why isn't my chalk magnetic? Well, the answer comes from Pauli. Pauli said, if you want to bring another electron, pop it right next to this one. Well, he said that second electron has to have the opposite spin of the first electron. So this electron has to be spin down if this electron is spin up, and they're going to be occupying the same orbital. So first of all, why? Well, the reason why this electron has to have the opposite spin is not because you just accept Pauli's exclusion principle. No, it's because you cannot write a wave function describing both of the electrons if you do not make the second electron spin opposite to that of the first one. So you literally cannot describe these two electrons quantum mechanically if you do not put their spins opposite to each other. So that's what Pauli's exclusion principle dictates. It says that the two electrons have to have opposite spin if they're going to occupy the same orbital. But that means that the two spins are going to cancel out and give a net magnetic moment of 0. So how do we have magnets in the universe if we have to always obey Pauli's exclusion principle? Well, the answer comes from valence electrons. You see, if you can somehow manage to create an unpaired set of electrons, well then voila, you don't have to obey Pauli's exclusion principle because that electron is unpaired. You're not going to put another electron next to that one. And so that electron is free to have a magnetic moment, which gives the overall atom a net magnetic moment. So let's break that down. Let's look at a specific case, iron. You see, iron has 26 electrons. So iron has 26 electrons. How are these electrons organized in its orbitals? Well, that's very simple to take a look at. See, iron is some kind of a metal, I believe. So what is the electronic configuration of iron? Well, we can start by writing down our 4 quantum numbers. Okay, these are the 4 quantum numbers that dictate the electronic configuration of iron. So we have the principal quantum number L, the angular momentum quantum number L, we have M, and we have the spin quantum number M sub S. So now here's the thing. If, for example, we're looking at the first energy level, then the angular momentum quantum number can be anything up to n minus 1. Okay, that's the maximum that our angular momentum quantum number can get up to. But m, this quantum number, can get between negative n minus 1 and positive n minus 1. So for example, if our principal quantum number was 2, then L could be either 0 or 1. And if L was 1, then M could be minus 1, 0, or 1, just as an example. And finally, M sub s, this last quantum number, the spin quantum number, is either minus 1/2 or plus 1/2. You can either have spin up or spin down. So now let's use this information to write the electronic configuration of iron and see why it has a net magnetic moment. So first thing I'm going to do is write down my 4 energy levels. So let's come over here. Hopefully you'll see what I write. So I'm going to go n equals 1, n equals 2, n equals 3, and if we have space, n equals 4. So I've got my 4 main principal quantum numbers written here. Now n equals 1. If we have n equals 1, then the maximum angular momentum quantum number can be 0. That's it. That's the only possibility. So L equals 0 is the only possibility. L equals 0 is also referred to as the s orbital. So if L is equal to 0, then we still have 2 possible combinations for the spin quantum number, right? You can have spin up or spin down. And so there you go. You've got your first 2 electrons placed in their orbitals. And so this is the 1s squared orbital. You have 2 electrons, spin up, spin down, occupying the 1s orbital. Now let's look at n equals 2. If n equals 2, then you can either have 0 for your angular momentum quantum number, which is the s orbital, or you can have 1 for your angular momentum quantum number. So L is equal to 1, which is the p orbital. But hang on a second. If L is equal to 1, then M can be minus 1, 0, or 1. So that implies we actually have not 1, but 3 different shells for our L equals 1 orbital. So L equals 1 has 3 different shells as follows. So now we can start adding the electrons to these orbitals. First, let's add 2 electrons here, 2 electrons here, 2 electrons here, and 2 electrons here. So this right here is the 2s squared orbital. So I'm going to write that here. This is filled up, 2s squared. And here we have 2, 4, 6. We have 6 electrons occupying these shells. So we write 2p to the 6th. And now let's consider the n equals 3 shell. So if n is equal to 3, well, as you might be guessing by now, we can have L equals 0, which is the s orbital, or we can have, let me now just write it like this. This is L is equal to 1. All 3 of them are L equal 1, which is p. And finally, we can have L is equal to 2 for the first time. So L is equal to 2 will have 5 degenerate orbitals. So this is L is equal to 2, which is the d sublevel. Okay, so why do we have 5 here? Because if L is equal to 2, then the m quantum number can be minus 2, minus 1, 0, 1, or 2. So now we can start adding our electrons in and see what the electric configuration is. First, I add 1 electron here, 1 electron here. Okay, that's pretty simple. That's 3s squared right there. Let's start adding in the electrons here. 2, 4, 6. Okay, that's pretty straightforward. That's 3p to the 6th. Let me write that here, 3p to the 6th. And now let's start adding in the electrons in my last level. Now, I have to start adding the electrons from lowest energy level to highest energy level, but these energy levels are all degenerate, meaning that they have the same energy. So I'm just going to start adding the electrons with an arbitrary spin up first. And now the last electron, I'm going to leave it. I can add it anywhere really. but it has to have an opposite spin. As you can see, it has to be spin down. So I've added my last electron right there. So let's see if I've added 26 electrons total. Right, so I've got all of my electrons right here in the picture. Now I can write the electron configuration of iron as 1s squared, 2s squared, 3s, oh yikes, I have to write 2p to the 6th, 3s squared, 3p to the 6th, 3d to the 6th, and 4s squared. So now, what do you see in this picture? This right here, this example right here captures the essence of magnetism. See, if you look at this picture, there's a few key ideas. First of all of these orbitals here, from n equals 1 to n equals 3, but up to 3p, all of these orbitals are what we call closed orbitals. These closed orbitals have zero net angular momentum. They have zero net spin. So these closed orbitals do not contribute anything to the magnetic moment of the atom. Why? Because all of the spins here cancel out. Spin up, spin down, spin up, spin down, spin up, spin down. So all of these closed orbitals, they contribute nothing to the net magnetic moment of the atom. But take a look here. First of all, we've got this 3d orbital. If you look at the 3d orbital, sure, this spin up and this spin down cancel each other. But look at this spin up, this spin up, this spin up, this spin up. These 4 electrons are all spin up and they're all unpaired. So that means these 4 electrons contribute to the net magnetic moment of the atom. In fact, that's why iron's net magnetic moment is 4 times the net magnetic moment of a single electron. Okay? Because these 4 electrons are unpaired. Now you say, what about the n equals 4 orbital? Well, the n equals 4 orbital, those electrons are like valence electrons. They're like lost puppies that don't have a leash, right? These electrons are no longer attached to the atom, really. In fact, they're kind of lost in the sea of electrons, as often is the case in a metal. So these n equal 4 electrons are not really part of the atom. They're more or less valence electrons that are free to float around in a sea of electrons. So these are the main characters. So these 5 orbitals, all of them are closed orbitals right here. So they do not contribute anything to the magnetic moment. And this 4s squared, these are the electrons of the metal, the valence electrons that are free to float away. All the action for the magnetic moment happens in this 3d orbital. And that's why iron has a net magnetic moment. It's because these 4 electrons are unpaired. So now the question becomes, why do spin pairs tend to align with each other? To answer that question, let's check out the next part. So now the next question is, why do spins tend to align? Why do these atomic magnetic moments tend to be in the same direction? Well, the reason why is because of 3 separate parts. First of all, there are 3 interactions we need to account for. If you have 2 electrons next to each other, there is first of all the Coulombic repulsion between the 2 electrons that we need to account for. That Coulombic repulsion happens to be smaller if the 2 electrons are aligned in their spins than if they're not. And nature always prefers the lowest energy state, the most stable state for a system. And so it's more likely to find 2 electrons with parallel spins than anti-parallel spins. And so therefore, the first thing we have to account for is Coulombic interactions. Coulombic interactions in the spin. The second thing we're going to account for is the Pauli exclusion principle, which says that you cannot have 2 electrons with the same spin occupying the same orbital. So the exclusion principle says that if you want to describe these 2 electrons with a consistent wave function, they must have opposite spin. So you have the Pauli exclusion principle to consider. And finally, the third interaction we've got to consider is that of the conduction electrons. Those electrons that we saw in the last level of iron, in the 4s squared level. Those electrons that are just valence electrons that are flying through the sea of electrons in the iron metal. And so that is the last interaction we have to consider, conduction electrons. So now if we combine all three of these interactions together and lump them into a single term, call it the exchange interaction term, then this term will help us describe how our magnetic moments respond to these three types of interactions, to Coulombic interactions because of electric repulsion, because of the Pauli exclusion principle, that the spins have to be opposite, or the two electrons cannot occupy the same orbital, or because of conduction electrons that are coming close and somehow interacting with our magnetic moment. Okay, so now let's finally get into the physics. Let's say we have a system of spins. So here is a kind of crystal structure. All right, so here I've got a crystalline structure with atoms of different spin. And now I'm going to explain a few key terms. First of all, if I take some of these atoms right here, and I consider their total magnetic moment, that total magnetic moment per volume is called the magnetization. Total magnetic moment per volume is known as the magnetization, capital M. Each of these atoms also, let's zoom into one of these atoms. Each of these atoms has a magnetic moment M, which has a magnitude of mu. Okay, and we have a total of, let's say, n atoms in this box. N atoms in this box. Right, so we've got this linear chain of atoms, each with a different spin. Some of the atoms are spin up, some of them are spin down. Let's say that we use the variable n plus to denote the number of spin up atoms and n minus to denote the number of spin down atoms. So then what is the total magnetic moment of the system? Well, we can say that if one of these atoms is spin up, for example this one, then it has an energy of mu times B, where B is the magnetic field that is external to the system. So here is my external magnetic field. So if the external magnetic field and the spin are parallel, then I just have mu B as my energy, right? So now if I have a total number of spins of n, where n is n plus n minus, right? It's just the number of spin ups plus the number of spin downs, then the total magnetization for my spin chain is going to be what? Well, I've got mu, and then I've got n plus contribution from each of the spins that are aligned with the external magnetic field, minus n minus for each of the spins that are not aligned with the magnetic field. And so now we can say, let me just divide both sides here by mu, then I have n plus minus n minus, and let's consider n plus plus n minus, which is just the total number of atoms in our spin chain. And so here we get that m over mu plus n times a half is equal to the number of atoms that are spin up in our chain. And now if I just add a minus sign, then I get the number of atoms that are spin down. And if I just simplify this a little bit by factoring out mu, then I get m plus minus, and mu is n plus minus. But what is n times mu? That's just the maximum magnetization. That's the magnetization that would occur if all the atoms in the spin chain were spin up. So if I had all of the atoms in the spin chain to be spin up, then I would have a maximum magnetization, M max, which is mu n. And that's exactly what we have here. And so this right here, n plus minus, is 1 over 2 mu times m plus minus the maximum magnetization. That's another way that we could write that right there. So now what we're going to consider is, in here, in this picture, we had no interactions, right? Now we're going to consider what the free energy for this system of spin chains is. Let's go ahead and check that. Okay, so now let's consider a single atom in an external magnetic field. So here's our atom, and here's our external magnetic field, B, that's in the positive z direction. Now, our atom could have one of two spins. It could be spin up or spin down. So our atom here could be spin up in alignment with our external magnetic field, or our atom could be spin down, anti-parallel to our magnetic field. Now, if our atom is spin up, then the total energy for our system would be mu dotted with B, where mu is the magnetic moment of my atom. Negative mu is the magnetic moment if the atom is anti-parallel. So here, since the two spins are parallel, I would simply have mu B for my total magnetic energy, and here I would have minus mu B. So now I can write down the partition function for this system. The partition function is simply going to be the superposition of the spin up and spin down possibilities. So I'm going to have e to the mu b over kt plus e to the minus mu b over kt. Now 1 over kt is usually abbreviated as beta in thermodynamics, so that's exactly what I'll do. This right here is beta, this right here is beta. And so now I can write that my partition function is e to the beta mu b plus e to the minus beta mu b. Okay, so now I've got my partition function. Now I can exploit this to figure out all sorts of properties about my system. First thing I can do is figure out the average magnetization, or the average magnetic moment for each of these atoms. Well, what's the average magnetic moment going to be? Well, it's simply going to be, let's see, it's going to be the direction of the spin, mu sub I, times the probability of the spin being in that direction. That's it. Well, what's the probability of the spin being in a certain direction? Well, let's say we consider the spin up direction, mu up. Well, the probability of the spin being in the up direction is simply the Boltzmann factor associated with that, which is mu b over kt divided by the partition function. And likewise, if we have a spin down, then we'd have minus spin down, right? Minus mu e to the minus mu b over kt, all divided by our normalization factor, the partition function. And so now if I were to just simplify this, then the average magnetic moment per atom would simply be, well, the magnetic moment upwards is just mu. So I'd have mu e to the mu b beta minus mu e to the minus mu b beta divided by my partition function, which I already know. It's simply e to the mu beta b minus e to the minus mu beta b. So this is what I have right here. And if I go ahead and factor out my mu, then what do I get? Something might be a little bit off here. This should be a minus sign indeed. This is minus mu beta, and z is actually plus. That's what's off. So now if I factor out my mu, my magnetic moment, then I obtain the following: e to the bub, e to the beta mu times the magnetic field minus e to the minus beta mu magnetic field divided by the same thing, but now with a plus sign. So e to the minus beta mu b. And you might actually recognize this. This is the hyperbolic tangent. So this right here is a hyperbolic tangent of our argument here, mu b beta. And all of this is multiplied by mu. And so this is the average magnetic moment for our atom. And so this actually gives us even more information that you might first expect. This right here tells us how the magnetization of our system changes as, for example, we change the magnetic field. But this is just for a single atom. What about more atoms? Well, if I have more atoms, then what would change is my partition function. How would my partition function change? Well, this is a partition function for one atom, and I know that the partition function is connected to the free energy of the system via minus kT times the natural log of the partition function. Now, if I take the partition function and raise it to the nth power, then I would obtain the free energy for an entire chain of these atoms. Let's do that. So if I raise this to the nth power, then I would get the partition function is e to the beta mu b plus e to the minus beta mu b to the nth power. And so if I raise it to the nth power, then what is this? Well, it might be a bit hard to tell at first, but this right here is just cosh. It's a hyperbolic cosine. Well, times a factor of 2 because there's no divided by 2 here. Of our argument, and all of this raised to the nth power is our new partition function. If we have now not one atom, but an entire chain of atoms. And so now I have my partition function. Now I can obtain my free energy quite readily. This is simply going to be minus kT ln of this, which is minus n kT times the natural log of 2 cosh beta mu b. And there you go. We have just obtained the free energy of this one-dimensional, non-interacting spin chain. So what's the moral of the story here? The moral of the story is that now we can figure out the net magnetic moment of our system by simply multiplying the average magnetic moment per atom by the total number of atoms. So if I go ahead and let's come over here. So take the total number of atoms, multiply it by my magnetic moment per atom. That's going to give me n mu times the hyperbolic tangent of bub, the beta 1 over kT, times the magnetic moment times the magnetic field. This right here is the total magnetization of my spin chain. So what information does this tell me? Well, if I go ahead and graph this, where should I graph it? Let's graph it right here. If I go ahead and graph this, graph the magnetization as a function of this argument here, bub beta ub, then I find something very interesting. So let's put this right here. What I find is as I increase the magnetic field or decrease the magnetic field, this is how the magnetization of the system changes. If the magnetic field is 0, then it turns out there is no magnetization for the system. In other words, if B is 0, so is M. The net magnetization of the system is 0 if the magnetic field is 0 externally. So that means if you don't apply a magnetic field, there's no preferred direction for the spins. They're just randomly, aligned in whatever direction, and they tend to cancel each other out. So now this is the entire picture for a non-interacting spin chain. Let's add in interactions. What do I mean by interactions? Well, when you have two electrons next to each other, there's all sorts of things that can go on, right? There's the Coulombic interaction, there's the Pauli exclusion principle, and there's those god-awful metalloid electrons that are zipping around the sea of electrons in the metal. So you've got these three interactions that are all part of the exchange interaction that are messing around with our magnetic moments. So we've got to factor that in somehow. So let's do that. Let's consider what the exchange interaction effect has on our spin chain. So here's my spin chain once again. So I have a chain of these atoms, and they each have a different spin. Okay, maybe this is spin up, maybe this is spin down, spin up, whatnot, right? Random spins I've just arbitrarily chosen. So now what I'm going to do is consider the interactions between them, but specifically only the nearest neighbor interactions, the nearest neighbor interactions between these spins. In other words, I'm going to think about how these two neighbors affect each other, how these two neighbors affect each other, how these two neighbors affect each other. What I will not do is consider how the first neighbor interacts with the third neighbor, or how the second neighbor interacts with the fourth neighbor, so on and so forth. I'm only considering the most basic possible interaction, nearest neighbor interactions, right? So how do I codify that? Well, first of all, let's consider the four possible types of nearest neighbor interactions. I could have a spin up chain, or I could have a spin down neighbor chain. So these are both examples of parallel alignment. I could also have an anti-parallel alignment, where one spin is up, one is down, or vice versa. One is down, one is up. Now, these parallel alignments tend to decrease the energy of the system because they're more stable, right? The coulombic repulsion is, the coulombic energy associated with parallel alignment, remember, is less than for anti-parallel. So I'm going to associate an energy minus J with these and an energy plus J with these. So how do I codify this into a Hamiltonian? Well, fear not, the answer is quite simple. The Hamiltonian for this system is simply going to be minus J times the summation over these interaction terms, right? Multiply these two, where omega or sigma, whatever this Greek letter is, sigma sub I represents the spin of the ith particle, of the ith spin. So for example, here omega sub 3 is plus 1, here omega sub 2 is minus 1. So just keep in mind that omega sub I is just plus minus 1 in all cases. So now this is what we have so far, but we've also got to factor in the idea that there's an external magnetic field B in the positive Z direction, right? So that's going to be accounted for by another term here, minus mu B, and then we're going to sum over how many of the atoms are pointing parallel or anti-parallel to the external magnetic field. Be very careful with your signs here. Notice that if my two spins disagree, if they're not in alignment, if they're anti-parallel, then I'm going to get a minus sign. Minus minus gets a plus, increasing the energy of my system, making that configuration less likely. Likewise, here, if I simply have a plus sign lowers the energy of my system, assuming that my magnetic field is up, which means everything is good, right? Because if the spin is up parallel to the external magnetic field, that system is more likely to occur. Okay, so here's my Hamiltonian thus far. Now, what can I do with this Hamiltonian? Well, the first thing you might think about doing is writing down the partition function, just as we did before. So let's go ahead and write down the partition function, which is summation of all the Boltzmann factors. So I have sigma sub I e to the minus beta times the energy, which is a function of sigma sub I. Now, what does this summation over sigma sub I mean? Well, it really means not one summation, but n summations over each one of the spins. So this right here is actually a summation of over the first spin, sigma sub 1, over the second spin, sigma sub 2, all the way up to the nth spin, sigma sub n. And in my argument, I have e to the minus beta times the energy, which is a function of sigma sub I. All right, so this is what we've got so far. So great. Now, how do we simplify this? Well, I can just plug in my Hamiltonian right here and see what I get. So let me do exactly that. So where can you see up to? You can see up to here. So let's start from here. So I can write that my partition function is, let's write down my summations over the first spin, second spin, all the way up to my nth spin. And then I have e to the minus beta. Instead of my energy, I can just replace that with my Hamiltonian here. So let's do that. minus j sigma I, and then I have my interaction term, sigma I plus 1, and then I have my magnetic field, external magnetic field effect term, which just counts how many of the atoms are parallel or anti-parallel to the external magnetic field. So great, I've got this. Now how do I simplify it? Well, first of all, one thing you might recall from elementary statistical mechanics is that an exponential raised to a summation is analogous to a pi product symbol. And so I'm going to exploit that here by now writing my partition function as z is equal to summation over all my spins, sigma sub n. And now I'm going to have this pi product from I equals 1 to n, where n is the number of spins in my chain. And so now things are going to get a little freaky. So I'm going to, hopefully, maybe if I move the camera back, you'll be able to see the entire math. So here I'm going to have e to the beta j sigma I plus 1 plus 1 half beta mu b sigma I plus 1 half beta mu b sigma I plus 1. All right, fantastic. We've got our entire partition function down. Let me just call this right here. This is a tradition, convention to call this entire thing right here, the entire argument of our product function, of our summation function, call that A. A, where A is some function of sigma I, the ith spin, and I plus 1. As you can see, it depends on both I and I plus 1. So what is the significance of this A term, right? What is the significance of A sigma I plus 1? Well, we can use this to write down a transfer matrix. That's the big idea. First of all, what I'm going to do is consider the following. Consider a spin. Consider just one term in this spin chain. So the summation over sigma sub I. So consider the following. Here we have a product, right? So we're going to be multiplying these A functions, right? We're going to be doing A sigma I plus 1, A sigma I plus 1, I plus 2, so on and so forth. So consider what would happen if we just had A sigma I minus 1 sigma I times A sigma I plus 1. What I'm going to do is claim that this product right here could be evaluated just as well by considering A as some kind of a matrix. You can consider A as a matrix with these elements. A is going to be a symmetric matrix that is governed by this 2 by 2 matrix right here. And so how do we find the elements of this matrix? Well, all we have to do is figure out what A plus minus, whatnot, all of that is. That's pretty straightforward. We just come back to our definition for this A function right here. So A plus plus, let's write it over here, A plus plus is simply going to be, so if you have plus plus, that means that sigma I is plus 1. Sigma I plus 1 is also plus 1. So that means you just have beta j, so e to the beta j. So sigma plus, if I have plus plus, then sigma I is plus 1. Sigma I plus 1 is also plus 1. So I have half beta mu b plus half beta mu b. That gives me a total of beta mu b. And that's what I have for A plus plus. And we can do something similar for A plus minus. For A plus minus, sigma I is plus 1, but sigma I plus 1 is minus 1. So I'm going to have e to the minus beta j. And then these two factors are going to cancel out. So that's all I have for A plus minus. And similarly, that's what I'll also have for A minus plus, because this is a symmetric matrix. And finally, for the A minus minus term, what am I going to have? Well, for that, I'm going to have minus 1 over here, and minus 1 over here, and minus 1 over here. That's going to give me e to the beta j minus beta mu b. All right, so I've got all of my terms for my transfer matrix. Now I can just write down my transfer matrix. So let's do that over here. My transfer matrix is e to the beta j plus bub, and my two symmetric elements are e to the minus beta j over here and over here, and my last element is e to the beta j minus bub. All right, so I've got my entire transfer matrix written down right there. Now all I have to do is figure out the eigenvalues of this transfer matrix. So let's do that. All right, so there was no eraser apparently in this room, so I'll have to do it analog style. So great. So now let's figure out what the eigenvalues for this transfer matrix are. So I'm going to go ahead and write my transfer matrix here. So my transfer matrix is e to the beta j. Now here it's convention to call this beta j k and this bub right here b. Okay, so I can write the entire thing quite simply as e to the k plus b, e to the minus k, e to the minus k, e to the k minus b. Okay, well that's not too bad, right? I've got the entire thing written quite simply down here. So now what we're going to do is, first of all, consider the fact that we can diagonalize this matrix, and we'll have, after diagonalizing the matrix, we'll have its eigenvalues written out right along the diagonals. So that means when we evaluate the partition function as the trace of a to the n here, then what we're really going to be doing is, instead of a to the n, I can write this diagonalized version of a n times. So I can write u minus 1 au times u minus 1 au n times, right? And what's that going to evaluate out to? Well, that's just going to evaluate out to the trace of this matrix to the nth power, which is fairly simple. It's just a diagonal matrix to the nth power. And the trace of this to the nth power is just lambda plus n plus lambda minus n. But now if we start out by assuming just arbitrarily that lambda plus is greater than lambda minus, because one of the eigenvalues have to be greater, then lambda plus to the n is much greater than lambda minus to the n, meaning that our partition function z is going to be more or less equal to the positive eigenvalue to the nth power, and that's going to be exact as n approaches infinity. So now that we've got that in our belt, once we figure out what our positive eigenvalue is, we can just plug it in to figure out our partition function, and then from our partition function we can get our free energy. So let's do that. So first thing I'm going to do is determine what the eigenvalue is. I've got my transfer matrix here. We just figured out that our partition function is essentially my positive eigenvalue to the nth power, and that's going to be exact as n approaches infinity, as the number of atoms in my spin chain increases infinitely. And so now all we have to do is figure out what this lambda plus is. So let's do that. So I'm going to go ahead and just evaluate the eigenvalues of this matrix. So I have e to the k plus b minus lambda, e to the minus k, e to the minus k, e to the k minus b minus lambda. And so the determinant of this is set to 0. So let's go ahead and evaluate that. So we're going to have e to the k plus b minus lambda times e to the k minus b minus lambda minus e to the minus 2k is equal to 0. And so let's see what we've got here. We've got e to the 2k minus lambda e to the k plus b minus lambda e to the k minus b plus lambda squared minus e to the minus 2k equals 0. Now let's bring out lambda squared here, and let's bring out minus lambda e to the k plus b minus e to the k minus b. And finally, I have plus e to the 2k minus e to the minus 2k equals 0. So now we can simplify this even further. See, if I factor out e to the k here, then what is this if not e to the b minus e to the minus b? And here I have e to the 2k minus e to the minus 2k. Well, these look very familiar. These are just sinh functions, right? So this is cosh of b, hyperbolic cosine of b, and this is sinh of 2k. Well, actually, it's 2 times cosh of b and 2 times sinh of 2k, since there's no prefactor of a half. And so I have lambda squared minus lambda e to the k times this plus this is equal to 0. So now I can treat this as a quadratic equation and just solve this quite easily. So here I have, for my quadratic, I'm going to have a is equal to 1, right? For lambda squared, a is 1. B is this thing right here, negative e to the k times the cosh of b, all times 2, right? And then finally for c, I'm going to have 2 times the hyperbolic sine of 2k. So now I've got all of that in my pocket, and I can write down the quadratic equation. So minus b, this is the weirdest quadratic equation you'll probably see in your life, but minus b plus minus the square root of b squared. So that's going to be 4e to the 2k cosh squared b minus 4ac. So a is just 1, but c is this right here. So minus 4 times ac, all divided by 2a. So that's just going to be 2. So this right here is lambda plus minus. So if I just take the positive root here, then I can write that lambda plus is equal to, dividing through by 2, e to the k cosh of b plus minus. If I take out a square root of 4, then I'm going to have 2 out here. I'm going to be left with the square root of e to the 2k cosh squared b minus 2 sinh 2k. Barring any mistakes, that should be correct. And so if that's lambda plus, then my partition function is just lambda plus to the nth power. So that's just going to be this mess to the nth power. So e to the k cosh b plus minus the square root of e to the 2k cosh squared b minus 2 sinh 2k, all to the nth power. And now that I've got my partition function, now I can get my free energy simply by virtue of F is minus KT ln Z. And thank you for watching, folks. That's it for today. All we have shown today is that the Ising model in one dimension has no phase transition because the free energy, which is just one step away from this partition function, is completely analytic, doesn't have any discontinuities.